All right, I'm back. We're going to now start looking at container 2. Now, container 2 has the same volume of 0.5 meters cubed, and the mass of water in it is 1.5 kilograms, so we have water instead of air, and the T is 20 degrees C. So the reason that this is different is that the water is not probably going to fill the container in liquid phase. Liquid phase of water has a density of 1,000 kilograms per meter cubed. Water, liquid, is 1,000 kilograms per meter cubed. So that's a lot. And we only have a half a meter cubed of volume here, but that means that it would take 500 kilograms of water to fully fill that container. And we have 1.5 kilograms of water. So we have nothing like enough water to fill that container with liquid. So what's really going to happen? Well, the liquid is not going to fill the container. The liquid is going to be sitting here at the bottom of the container. It'll fill it up to some depth. We can call that depth D if we want. It doesn't matter what we call it. There's D for depth. And so there's going to be water sitting at the bottom of the container. Does that mean the top of the container is going to be empty? Well, it could be a vacuum there, right? So you could say, well, maybe the water just goes to the bottom. 20 degrees C, water is a liquid, so it's not going to boil at 20 degrees C, is it? Well, actually, it is going to boil at 20 degrees C because if it were a vacuum there, then the pressure inside that chamber would be lower than the boiling, the saturation pressure for 20 degrees C. So how do you know that? Well, you go onto the steam tables in any thermodynamics book, and you can see that. So you can find that, as you know, but I'll show you here once anyway. Try to find my steam tables in this book. I got some thermal book, just a random thermal book that I found. There's a pressure table. And I'm trying to find the temperature table. So here's the temperature table. I'll put it up here quickly. You can see it. Hopefully you'll be able to see a little bit. I think I can zoom in here and you can see it better. Well, I'm here. I'm on the saturated table. This is the saturated liquid table. And you can see that at 20 degrees Celsius, water will, the pressure to keep it from boiling is 2.339 kilopascals. So 2.339 kilopascals is what we call the saturation pressure at 20 degrees C. So I'll write that down here. We'll zoom back out. So at T equals 20 degrees C, P saturation is equal to 2.339 kilopascals. Now, that's not a lot of pressure. There's in this room right now is atmospheric pressure. Atmospheric pressure is about 101 kilopascals. So it's 50 times greater than this. And that's why water doesn't boil when it's just sitting in the room. When it's sitting in the room at 20 degrees C, there's plenty of pressure from the air to keep that water from boiling because the pressure in the room is 101 kilopascals roughly. And you'd have to lower the pressure all the way down to 2.339 kilopascals before you'd see any boiling if you keep the water at 20 degrees C. But in the container we just drew, we're speculating about whether there's a vacuum up here. If there's a vacuum up here, then of course the water will boil because the vacuum pressure is less than 2.339 kilopascals. The pressure of a vacuum is 0. So if you have an empty container, a truly empty container, and you have some water in it, that water is going to boil at almost any temperature except absolute 0. So the thing is going to boil. And if it boils, then it's going to keep boiling until either you run out of water, that is, all of the water turns into a vapor phase, or you reach saturation pressure. In this case, I suspect that we will have enough water in this container to reach saturation pressure. And we'll verify that by calculating volumes later. But if that's true, if we have enough water, it will boil in the vacuum until P equals P sat at T equals 20 degrees C. So it guys won't be a vacuum anymore after it starts boiling. There'll be some water in there, in that open space up above. We'll have some water, but as long as the pressure is below 2.339 kilopascals, the water will keep boiling. And then it will stop boiling when the pressure in the top of the container, in that open space in the top, becomes saturation pressure. So it'll reach 2.339 kilopascals. So that's the answer to the top pressure, provided that we have enough water. We'll verify that we do later. All right, well, that's good, but we need to know how much water is boiled off and how much water is sitting in the bottom. So we don't know that yet, so we're going to go ahead and try to figure that out. So we know that the volume of the fluid-specific volume for liquid water is 0.001 meters cubed per kilogram. This you could look up in a table or you could remember it. Liquid water has a very stable density. It's 1,000 kilograms per meters cubed under most conditions. So this is the obviously 1 over that for your specific volume. The gas volume, again, you look up on the steam table. Same table I was looking at before. You look it up under the saturated state. And the specific volume you will see for liquid water vapor at 20 degrees Celsius is 57.79 meters cubed per kilogram. We also know the total volume in the tank, right? The total volume in the rigid container is 0.5 meters cubed. So that has to be a combination of both volumes, the volume of the liquid and the volume of the gas. And you know how to do this from thermal. You use the mass fraction X and you multiply that by the liquid volume, and then you add the 1 minus the mass fraction times the liquid volume, and then X times the vapor volume on a specific basis. So 1.5 kilograms times this mix of liquid volume and gas volume, that's got to equal 0.5 meters cubed because the whole container has to be full with 1.5 kilograms of water. So we know these numbers because we just wrote them down. So it's 1.5 kilograms total. Has to be 1 minus X times 0.001 kilograms plus X times 57.79 kilograms. So that's our simple equation. It has one equation and one unknown. The only unknown is X. So I can solve for X. So I first gonna bring the 1.5 over to the other side, 0.333. That's meters cubed per kilogram. Has to equal 1 minus X times 0.001 kilograms. Kilograms per meter cubed. Meters cubed per kilogram. This is not kilograms here. This is meters cubed per kilogram, and this is meters cubed per kilogram. My bad. So meters cubed per kilogram plus X times 57.79 meters cubed per kilogram. Obviously, all those units check. They match each other. So now we're just solving for X. X is unitless. It's just a mass fraction. So you end up with 0.333 equals 0.001 plus 57.789 X, or X equals 0.333, actually it should be, 332, divided by 57.789. And that equals 0.332 divided by 57.789, 0.00575. You carry 3 sig figs here. So that's my mass fraction. So very, very little of the water is in the vapor phase. This is a very small number. So 0.575% of water is in vapor phase or is in a gas phase. and a huge, huge amount of it, 99 point, what is that? 99.425% is in the liquid phase. So that's how much mass fraction is in gas versus liquid. So a very, very tiny, tiny fraction of the water boils, but that boiling does cause the pressure to change in the box. So instead of being vacuum pressure, the pressure is whatever we said it was, something, saturation pressure. So now the question is, with this liquid in the bottom of the box, is that enough to change the pressure at the bottom versus the top? So we've got the box here. It's got a top pressure, which was whatever we said it was before. And the bottom pressure is going to be a little bit greater because there's this liquid layer sitting on top. And it's going to be greater depending on the depth of that liquid layer. And we know that the pressure difference is going to be, once again, rho g, and this time we're going to call it d. So rho g is going to be the pressure difference between the top pressure in the box, the vapor phase pressure, which was that saturation pressure, and the bottom pressure in the box, which is underneath a thin layer of liquid water. But we don't know how thin that layer is yet. So now we're going to try to calculate that. So we're going to say, all right, well, the total volume of the liquid layer is equal to the specific volume of the liquid times the total mass of the liquid. And the total mass of the liquid is 0.99425, which is the mass fraction, times that 1.5 total kilograms of liquid. So that's going to come out to be 0.99425 times 1.5. 1.4913 kilograms times this specific volume of the liquid, which is just 0.001 meters cubed per kilogram. Can't fit that in there. But that's just going to be equal to 0.00149913 meters cubed. So we're not going to carry all those units. We'll drop it at 3 sig figs. So we'll go with 0.00149 meters cubed of liquid. So that's how much volume of liquid we have. And now the question is, how deep is it? So once again, we need to know, how big the container is, and we'll again assume, maybe it's a little bit like a cube. So if that's true, then the liquid volume is going to equal the depth of the liquid times the length squared of that cube. And we decided that the length had to be 0.794 meters roughly for a cube to be that size. And so we can calculate D based on that. And if you do that, putting this 0.00149 meters cubed on the left for the liquid volume is equal to D times 0.794 meters squared. And you solve that for D, you get that D is equal to 0.00236 meters. So D is very small. D is 2 millimeters. D equals 2.36 millimeters. So a very, very small liquid layer, only a little over 2 millimeters thick, because water is just so heavy, so dense. So we're going to throw out, going to see if that can cause a significant pressure change. So delta P here we said was equal to rho g d. Well, we have all those numbers now. So rho is 1,000 kilograms per meter cubed. G, of course, is still 9.81 meters per second squared. And the depth we said was 0.00236 meters. So adding all those numbers together, we get that the pressure change is equal to 23.2 newtons per meter squared. Now, interestingly, that's about the same thing we calculated for the top to the bottom pressure difference in the box with air in it, but that's just a coincidence as far as I can figure. But is this significant in this situation? We said with air it was definitely not significant because it was such a tiny, tiny fraction of the pressure in the box. is really below it was below the number of sig figs we were carrying. In this case, it's close. The top pressure, we calculated that to be we didn't calculate it, we looked it up because it was a saturation pressure. It was 2,339 newtons per meter squared. So that's 2,000-ish. And, the bottom pressure in this case, it is within the sig figs we've carried because this 23 is going to go right in there. So it would be 2,362 newtons per meter squared. So it is a slight difference, 2,339 to 2,362. That 23 newtons per meter squared actually can be seen, at least in this case, because the pressure in the top of the box is actually quite low. That 2,339 newtons per meter squared, of course, is very low pressure because it's the pressure that you can boil water at when it's only at 20 degrees Celsius, and that's a very low pressure because water doesn't boil very easily at 20 degrees Celsius. All right, so that's the answer. You have a box that has liquid water on the bottom, just about 2 millimeters of water on the bottom, and the rest is filled with water vapor, but most of the mass is actually in the liquid water phase, very small amount of vapor, and a very small difference in pressure between the top and the bottom.